Hey guys, my name is Talia. I'm a staff member at Discovery and I'm going to help you do your homework today. Okay, so this question is called difficult correlation coefficient. And that's because it's a little bit difficult, right? Because you're used to finding the correlation coefficient when they give you the average, they give you the standard deviation. You have a lot of numbers already given to you and you can use those to find it. But in this question, all you have is a list of x and y values and you have to somehow get to your correlation coefficient R from those. But what do we know about the equation for R, right? Let's just look at what it is. So the equation to find the correlation coefficient is the sum of all zx, z-scores for the x, times the z-scores for the y, over n, the number of pairs. We have n by counting, but we don't have zy and zx. And to go a step further, how can we find zy and zx? Look at the equation for a z-score. To find any zx, you do the value you have minus the average for x over the standard deviation for x. And it's the same thing for y. You just switch the x with the y. And so what do you not have here? Well, I guess we have all the x values, but we don't have an average and we don't have a standard deviation. But the good news is we can actually find the average and the standard deviation with our data points. We've done that a million times before. So basically in this problem, all you have to do is find your equation and kind of work backwards until you get to a point where you can start plugging things in and eventually getting to this value. So what I like to do with this problem to keep track of all the different values I'm calculating is make a couple new charts. And so the first new chart I'm going to make is just to keep track of these initial values that we're calculating. So we can do for each x and y, record the average and the standard deviation. And you guys know how to take the average, but I'll do it with you. We do 1 plus 2 plus 3 plus 4 plus 5 plus 6. I picked these numbers on purpose because I don't want to deal with annoying ones. And then you divide by n, which is 6. The average for x is 3.5. And then the standard deviation is a bit more complicated. Here, I'll write out the equations for both here. Average equals sum of all values over the number of values, and standard deviation, that's a little more complicated. You do the sum of all values minus the average, or I'm just going to write average, that's what I've been doing, squared. So you take every value, subtract the average, square that, do it for every value, and then add it up at the end. And then you divide by the number of values. And so in this case, the standard deviation is, so you do 1 minus 3.5 squared plus 2 minus 3.5 squared plus So we got about 1.7078. You can probably should just keep the pure value instead of rounding in the middle of the problem because that can cause problems, right? Then we do the same thing for y. You sum up all y values and divide by the numbers. So 2 plus 4 plus 6 plus 4 plus 2 plus 1 divided by 6. About 3.167, right? And then we can do the same thing to find standard deviation of y as I showed you before for the x, so I'm not going to go through that again. Okay, so for the same calculations, you get that the standard deviation for y is about 1.675-ish. All right, this is the first step. You have these values. Guess what? You can start finding all of these z-scores. And yes, it's kind of a pain in the butt. It's going to take you a little while, but they told you it was going to be difficult. So I'm going to demonstrate how to find just one of these z-scores kind of as an overview, and then obviously you go through and repeat the process for all 12 numbers you have. And now that we're starting to calculate the z-scores, this is where I like to draw my second chart, which is you have your x and y, and then for each pair, you calculate your z-score for the x and your z-score for the y. And then, oops. You have a column 4, and because you're multiplying the z-scores together for all these pairs, and then adding them up, I usually do a column for zx times zy, so you just multiply it across to get this. And then, at the end, I just sum up this column. So, we already know our x and y. 1, 2, 3, 4, 5, 6. And now we're going to calculate these. So for this first one, what you do is you already have the average in the SD. Take the first value 1, subtract the average, which is 3.5, and then divide by the standard deviation, which is 1.7078. And you get about negative 1.46, which, do a reality check, that makes sense because 1 is pretty significantly less than the average of 3.5. So on a normal distribution curve, if this is 3.5 at the average, right? If you want to go all the way down to 1, that's going to be pretty far in the other direction, and it'll have a pretty big negative z-score. So that's how, as you go along, you can kind of do a reality check on yourself to make sure you're not making a mistake. Because the issue with this problem is you're calculating a lot of small, little values, and if you mess up one of them, it's going to be wrong. So just kind of try to check your work as you're going. So now I've calculated all the z-scores for the x values, all the z-scores for the y values, and in addition, multiplied each pair together to find zx times zy. So now all that's left to do is sum it up so we can find our numerator for the correlation coefficient equation. But before I go to that, I want to give you guys one more tip. If you notice here that there's a couple repeat numbers, in the y column, and you don't have to calculate the z-score for that twice. It's obviously going to be the same for both numbers. So you can kind of skip that. And then also, if the number is the same distance from the mean, but on opposite directions. So for example, say your mean is 4, and then this is your mean, and then you have a value before it that's 3, and a value after it that's 5. These are going to have the same z-score, but opposite signs. So because this one's lower, this one will have a negative z-score, and this one's higher than the mean, so it'll have a positive z-score, but the same value, if that makes sense. So you can kind of cheat it that way, and I did that here. 3 and 4 are the same distance from 3.5. They're both 0.5 away, just 4 is 0.5 more, and 3 is 0.5 less. So they have the same z-score, but opposite signs. This one's negative 0.29, and this one's positive 0.29. So if you can recognize patterns in this while you're doing it, you can make this question a little bit less difficult. That's just one tip from me. Okay, but now on to actual business again. We're going to add up all these values. So let's add up 1.01 plus negative 0.44 plus negative 0.49 plus 0.14 plus negative 0.61 plus negative 1.88. And we get negative 2.27. Okay, so that's good news. We're almost done. We have our numerator here. So, to find our r, we take our sum and divide by n, the number of pairs we have, which is 6. In this question, I think it's always going to be 6. And we get, as the grand finale for our r, pretty low correlation, negative 0.378. That's rounded to 3 decimal points. And one quick reality check, is this number in between negative 1 and 1? And yes, it is. This is a valid correlation coefficient, and we found it.